Welcome to this explainer. Okay, so today we're diving into one of the absolute coolest engineering battles going on right now, the quest to shrink the supercomputer. I mean, just imagine, you want the raw visual processing power of a massive, high-end desktop PC, but you have to cram it onto a tiny little battery. How on earth do we actually pull that off? Well, we're going to look at two completely radically different solutions that are literally pushing the boundaries of what our mobile devices can actually do.
Seriously, let's just think about this for a second. How do we fit a supercomputer into a tiny, fast-flying nanodrone, or a sleek pair of augmented reality glasses? These devices have to process massive amounts of visual data instantly, so they don't just crash straight into a wall, or so they can cast realistic lighting right there in your living room. But they're incredibly tiny. They don't have power cords, and they definitely do not have giant cooling fans. That is the core dilemma we're going to unpack today.
All right, let's dive into this. Here's our roadmap for today. First, we'll hit the mobile computing dilemma. Second, putting brains on sensors. Third, outsourcing to clouds. Fourth, a really surprising perception loophole. And finally, the future of mobile vision.
Section 1. The Mobile Computing Dilemma.
To really get this dilemma, we have to start with cold, hard physical reality. Now, you might be thinking, hey, because of Moore's law, mobile devices are just naturally going to catch up to desktop PCs, right? Just give it time. Well, actually, look at these strict physical constraints. Mobile devices have a tiny form factor, which means severely limited computing power. They are restricted by super tight energy budgets because of those small batteries. And critically, they have massive weight and thermal limits. I mean, you literally can't strap a heavy heatsink to a pair of AR glasses without burning the user's face. So because of these physical limits, engineers can't just brute force their way out of this. They need some incredibly clever workarounds.
Moving to Section 2, Path 1, Brains on Sensors.
And that brings us to our very first clever workaround, edge computing. Basically, putting the processing power exactly where the data is being gathered. To see why this edge processing is so crucial, we need to look at a massive computational burden called optical flow. As defined here, optical flow is the movement pattern of pixels or edges caused in a visual scene by the relative motion between an agent and a scene. Essentially, it tracks how things shift from one frame to the absolute next, so the device actually knows how it's moving through space. Calculating this for every single pixel, frame after frame after frame, it takes an enormous amount of math. Trying to do this on a traditional centralized CPU would totally drain a small drone's battery in just a few minutes.
And this brilliantly illustrates the solution cooked up by researchers at ETH Zurich and ST Microelectronics. Just take a look at the VD56G3 image sensor. Notice how unbelievably tiny it is next to that 2-centimeter scale? It's wild. Instead of sending raw visual data off to some separate processor, this sensor features an embedded application-specific integrated circuit, an ASIC, so it essentially has a localized brain built right into the camera itself. All that heavy, intense optical flow math happens directly on the sensor, before the data even thinks about moving anywhere else.
So what does this all mean? Well, the crucial point here is performance. By putting the brain right on the sensor, this hardware acceleration achieves blazing speeds. Researchers clock this tiny chip processing up to 300 frames per second at lower resolutions. For a fast-flying nanodrone trying to navigate a complex room, or AR glasses that need to instantly react to your rapid eye movements, that ultra-low latency is absolutely crucial. It basically means you get the mathematical answer before the drone has a chance to crash into a tree.
But what's really fascinating here is the energy efficiency. Check out this power draw comparison for high-resolution 60 frames per second stream. With the optical flow calculation completely turned off, the sensor draws about 176 milliwatts of power. And when you turn that massive mathematical calculation on, it only jumps to about 220 milliwatts. Guys, that is a difference of roughly 43 milliwatts. This data proves exactly why edge computing is such a game changer. You're getting high-end computer vision for an incredibly tiny fraction of a watt.
And amazingly, you aren't sacrificing quality for that super low power draw. The data here compares the displacement tracking of this tiny optical flow camera against a gold standard Vicon motion capture system, which is used as the absolute ground truth. Just look at how tightly those lines map onto each other. Even while sipping mere milliwatts of power, the sensor tracks the movement with astonishing accuracy.
It totally proves that putting the brain directly on the sensor is a massive win for mobile robotics.
Section 3, Path 2, Outsourcing to Clouds.
But what if the math is just too huge? What if it's so incredibly complex that it can't possibly fit on a little edge chip? Well, let's explore a system called CloudLight, developed by researchers from NVIDIA and Williams College. Their big goal was to render realistic, global, indirect illumination in real time. Think of how light bounces off a red carpet and casts this subtle, realistic red glow onto a nearby white wall. Calculating all those tiny light bounces requires massive compute power. So what was their solution? Amortize it. Basically, they take the heavy burden of simulating that bouncing light and beam it out over a network to remote servers.
Notice the striking contrast here. On one side, you've got this heavy, power-hungry desktop PC, and on the other, a sleek, lightweight tablet. But both are displaying a beautifully lit, super complex 3D scene. How? The cloud bridges the gap between them. Instead of the tablet instantly draining its entire battery trying to compute billions of light rays, it completely outsources the hard math. The cloud essentially acts as a giant remote brain, allowing these small, cordless devices to display stunning cinematic graphics.
Now, what's really interesting about this slide is how they divide the labor. Walk through this CloudLight pipeline with me for a second. The heavy lifting for the indirect lighting, that's the blue sections over on the left, stays entirely on the cloud server. So whether they're using voxel tracing or photon mapping, the massive server is the one crunching those numbers. It then streams just the finished lighting data across the network to the local device on the right, the black section, which just handles the final display. The local device barely even breaks a sweat. Section 4, the human perception loophole.
But hold on a second. Anyone who has ever played a multiplayer game knows that network lag can completely ruin the experience, right? If you move your head in an AR headset and the lighting takes a full second to update, you are getting instantly motion sick. So how is this cloud system actually usable in the real world? Well, the researchers discovered an absolute aha moment. They found a magic number, 500 milliseconds, half a second. Now, in computer graphics, half a second is usually a total eternity. So why is this specific number so incredibly important?
Let's read this quote directly from the researchers. They state, "Up to half a second of the latency in indirect illumination is visually acceptable and, in fact, hard to notice." Now, the researchers themselves admitted they actually started this project as skeptics. They thought network lag would be an absolute showstopper, but they were completely shocked to discover this psychological loophole. You see, the human eye easily detects when a solid object stutters or lacks, but when the shadows and the bouncing light lag by half a second, our brains simply do not process it as an error. By exploiting this massive flaw in human perception, remote rendering actually works beautifully, totally bypassing the physical hardware limits. Section 5. The future of mobile vision.
Looking at the future of mobile vision, the crucial takeaway here is that neither the edge nor the cloud is the single ultimate winner. Actually, they're two complementary tools that solve totally different parts of the exact same problem. As we see in this comparison, we absolutely need edge acceleration for split-second reflexes, like a nanodrone adjusting its flight path at 300 frames per second using mere milliwatts of power. But at the same time, we need cloud rendering for massive visual quality, like beaming hyper-realistic lighting into an AR headset without melting the battery. Both of these paths succeed because engineers found some truly brilliant workarounds, hardware specialization on the edge, and psychological loopholes in the cloud.
Which leaves us with this final, genuinely fascinating question to think about. What will be the next big perceptual loophole engineers exploit to leap forward in mobile computing? I mean, if we can literally hide half a second of lag right in our shadows without anyone noticing, what other blind spots in human psychology can we use to cheat the physical limits of our hardware? It is such a thrilling space to watch. Thanks for joining me on this explainer, and keep questioning how the amazing technology around you is actually built.